Okay, so now we are going to talk about the kinetics of enzyme catalyzed reaction. But before that, we are going to look at a few basic terminology and ideas in this regard. So this is a generalized expression showing the conversion of a substrate into a product. The substrate is being converted into a product, and the rate constant for this reaction is represented by K. So the rate of reaction, that is how much substrate is being converted into product in a given interval of time. So that is the rate of reaction, and the rate of reaction is given by this expression, which is the rate constant times the substrate concentration. In case of enzymes, the rate of reaction is also referred to as the velocity of the enzyme catalyzed reaction. So the word velocity means the rate of reaction. So the velocity of enzyme catalyzed reaction, or in other words, the rate of enzyme catalyzed reaction, will be given by this expression, which is the rate constant multiplied by the concentration of the substrate. The enzyme binds to the substrate and forms the enzyme substrate complex. This is a free molecule of enzyme which binds to the substrate and forms this enzyme substrate complex. The enzyme then converts the substrate into the activated complex, the transition state, and then eventually converts it into the product. The product is then released from the active site of the enzyme. So when the enzyme converts the substrate into the product, it releases that product, and now this molecule of enzyme is again free to bind to another molecule of substrate and therefore catalyze the reaction again. So in this way, the enzyme, which is the catalyst, is participating in the reaction, but it is not consumed during this reaction. So at any given instance, the total amount of the enzyme present in a reaction mixture will be made up of these two populations: the free enzyme molecules, which are not bound to the substrate, and the enzyme molecules which are bound to the substrate, forming the enzyme substrate complex. Initially, when the reaction starts, all of the enzyme is existing in form of free enzyme, and when the substrate is available, the enzyme bind to that substrate. Initially, when the reaction starts, the concentration of free enzyme is more, so therefore the rate of reaction is called as the initial velocity, or the initial rate of reaction. However, after some time, when the concentration of enzyme and substrate is such that the substrate is present in excess, so that when the enzyme molecules, they release the product and free enzyme is produced, now more substrate is available to bind to the enzyme. So in this way, when the reaction is progressing at such a concentration of substrate that when free molecules of enzyme are released, they immediately combine with the substrate and reform the enzyme substrate complex again. So this is the time at which the enzyme is operating at its maximum rate of reaction. So this is called as the maximum velocity of the enzyme, which is depicted by this expression Vmax. At this particular concentration of the substrate, where it is surplus, so that whenever free enzyme molecules are released, they can again combine to the substrate and form the enzyme substrate complex. So at this particular concentration of the substrate, the enzyme substrate complex is maintained at a constant concentration. Such a concentration of the substrate is called as the saturating concentration, because at such a surplus concentration, such a high concentration, the enzyme molecules, they exist in the form of enzyme substrate complex, because the sooner an enzyme molecule is released as a free enzyme, it is going to be bound by another substrate molecule to reform the enzyme substrate complex. This is diagrammatically represented here. On the x-axis of this graph is the concentration of the substrate in the units of concentration, millimolar in this case, and on the y-axis is the rate of reaction, which is represented by the reaction velocity. It is depicted in terms of micromole per minute, that is, the change of concentration of the substrate into product per unit of time. So you can see that initially when the substrate is zero, the reaction rate is also zero. As the substrate concentration increase, the rate of reaction also increases. And eventually this forms a hyperbolic curve. And at a certain concentration of the substrate, when the substrate becomes saturating, it becomes surplus. So now the rate of reaction, it eventually becomes the maximum rate of reaction. Another very important concept regarding the kinetics of enzymes is the assumption of steady state. Steady state, the word steady means constant, maintaining. So the steady state is a state which refers to the constant concentration of the enzyme substrate complex. This is represented by this graph here. On the x-axis is time, and on the y-axis is the concentration. So here you can see that this is representing the substrate concentration, and this green line is representing the concentration of product. When the reaction starts, the substrate is present at its maximum level, and then gradually the substrate is going to be converted into the product with the passage of time, so its concentration keeps on decreasing. This green line shows the concentration of the product. As the reaction progresses, the concentration of the product increases because the substrate is being converted into this product. Here, this orange line shows the enzyme substrate complex. Initially, when the reaction starts, the enzyme substrate complex, its concentration is low. But when eventually the amount of substrate is saturating, so therefore the enzyme molecules which are released, the enzyme molecules which complete a reaction and they're released, now there is sufficient amount of substrate available so that these free enzyme molecules again are bound by the substrate and are converted into the enzyme substrate complex. So in this way the cycle continues. Free enzyme binds to the substrate, is converted into the enzyme substrate complex, converts it into the product, free enzyme is released, and eventually it is going to bind again to the substrate. So that means that at this particular concentration of the substrate, when it is saturating, the concentration of the enzyme substrate complex is maintained. It remains steady. This is diagrammatically represented here in this graph, that initially when the reaction starts, the concentration of enzyme substrate complex is low, but as reaction progress, the concentration of the enzyme substrate complex, it remains constant. So this particular condition is called as the steady state. It is the region, it is a part of the reaction where the concentration of the enzyme substrate complex remains constant. Alright, so with this basic background information that the enzyme binds to the substrate and it catalyzes the reaction, the rate of reaction is called as the enzyme velocity. And also we have talked about the steady state, that at saturating concentration of the substrate, the concentration of enzyme substrate complex remains same, remains constant. So with this background information, now we are going to proceed to the enzyme kinetics and the derivation of the Michaelis-Menten equation. This is an equation representing the chemical reaction taking place, that enzyme binds to the substrate and forms the enzyme substrate complex. The enzyme substrate complex, this part is a reversible reaction. The reaction can proceed both in the forward direction as well as in the backward direction. So substrate can bind to the enzyme and it can result in formation of the transition complex, or it may dissociate again as well. So the rate constant for this forward reaction is given by K1, and the rate constant for this reverse reaction, that is the breakdown of ES, that is given by K minus 1. In different textbooks, these representations may be different. This one is taken from Lehninger Principle of Biochemistry. Then when the enzyme substrate complex is formed, the transition state is achieved, and eventually the substrate is converted into the product. So this reaction is given by the rate constant K2. So the rate of reaction is given by the rate constant multiplied by the concentration of the reactant. For this part of the reaction, the reactant is the enzyme substrate complex. So therefore the rate of reaction will be given by this expression, rate constant K2 multiplied by the concentration of the reactant, which is the enzyme substrate complex here. Now we have talked about the steady state. The steady state says that at a given concentration of the substrate, when it is saturating, the concentration of the enzyme substrate complex remains constant. So that means the rate of formation of the enzyme substrate complex is equal to the rate of the breakdown of the enzyme substrate complex, because the concentration of ES is constant. So the rate of formation is equal to the rate of breakdown. Now, the rate of formation of the enzyme substrate complex is given by this expression K1. So this is the rate constant K1 multiplied by enzyme concentration multiplied by substrate concentration. These are the two reactants. So the rate constant multiplied by the concentration of the reactants would give the rate of formation of enzyme substrate complex. At any given instance, it is difficult to find the concentration of the free enzyme. So therefore, this free enzyme is expressed in this following way. The total amount of enzyme is equal to the sum of free enzyme plus the enzyme which is bound by the substrate. So the equation could be rearranged to find the free enzyme, which will be equal to the total enzyme concentration minus the enzyme substrate concentration. So total enzyme minus the engaged enzyme would result in giving the concentration of the free enzyme. So this expression, the free enzyme, this expression is given in this form: total enzyme minus enzyme substrate complex. So this is the rate of formation at the rate constant K1 for the forward reaction. This shows the free enzyme and this shows the substrate concentration. So therefore this equation gives the rate of formation of the enzyme substrate complex. Now there are two ways the enzyme substrate complex can break down. One is the reversible reaction, where the substrate is going to be dissociated, and the other one is the forward reaction, where the enzyme is going to be converted into the product. So there are two ways that the enzyme substrate complex can break down. This is given by the reverse reaction K minus 1. K minus 1 is the rate constant for this reverse reaction. So the rate constant for the reverse reaction times the ES concentration. So this is one way the breakdown can take place. The second way is the forward reaction. K2 is the rate constant and it will be converted into the product here. So this is for the forward reaction, K2 times ES. Now, because of steady state assumption, we know that the substrate concentration is such that the rate of formation of the enzyme substrate complex and the rate of breakdown of this complex are equal to each other. Therefore, the concentration of the enzyme substrate complex is constant. Since these two rates, the rate of formation and the rate of breakdown, are equal, so we put these two in this equation. So this part shows the rate of formation K1 times free enzyme times substrate equals K minus 1 ES, which is the reverse reaction, and K2 ES, which is the forward reaction. So these two parts, they show the rate of breakdown, and this shows the rate of formation of the enzyme substrate complex. So now we simplify this. So we multiply K1 with this expression here. So it becomes K1 ETS. So this is K1 ET multiplied by S. So that becomes K1 ETS. The other part of this expression is K1 ESS. So this becomes K1 ETS minus K1 ESS. And on the other side of the equation, we take the term ES common from these two. So therefore, that becomes K1, K minus 1 plus K2 multiplied by ES. ES is a common term in both of these. So this is represented here. So what we have done here is that we multiplied this expression with K1 and we have taken ES common from the other part of the equation. So this turns into K1 ETS minus K1 ESS equals K minus 1 plus K2 times ES. Now we add this term K1 ESS to both sides of the equation. So when it is added here, this will this will be cancelled. So we get K1 ETS here equals K1 ESS, so which is added to this side of the equation, plus K minus 1 K2 ES, this part. And now again we take, since ES is again a common factor in both of these terms here, so again we take ES common from here, so we are left with K1S plus K minus 1 plus K2 whole times ES. So ES is a common term in this expression. So next we solve this equation for ES. So therefore this entire expression is taken to the other side of the equation here. So that would give us the value of ES, which is the enzyme substrate complex. So ES here will become K1 ETS, which will be the numerator here, divided by this expression, which is the denominator here, K1S, K minus 1, K2. Now we further simplify the denominator of this equation. So this is the denominator of the equation shown here, K1S plus K1, K minus 1 plus K2. So we divide this entire denominator by K1. So when we divide it by K1, so K1 by K1 will be cancelled. That will become S, and rest of the expression will be K minus 1 plus K2 here, divided by whole divided by K1. So this will become the denominator of this equation. K2 is the rate of forward reaction. K minus 1 is the rate constant for the backward reverse reaction. These two are representing the rates of the breakdown. K1 is showing the rate of synthesis as depicted here. K2 and K minus 1, they both are representing the breakdown of enzyme substrate complex, and K1 is the rate constant for the formation of enzyme substrate complex. So if you look here, you can find that this is a ratio of the rate constants. This part is the ratio of the rate constants for the breakdown of enzyme substrate complex and the formation of the enzyme substrate complex. This collectively, these three, so collectively these three rate constants, they are represented by another constant which is called as Km. Km is actually the ratio of the rates of the breakdown and to the rates of the synthesis of the enzyme substrate complex. So this is these three constants are expressed collectively in form of another constant which is called as the Km. Km is called as the Michaelis constant. So therefore the equation is now converted into this form: Es equals ETS divided by S plus Km. Now, previously we have seen this, that the rate of reaction is given by this expression, V naught equals K2 times ES. So we put the value of ES from the previous equation into this equation. So now the rate of reaction will become K2 times ETS over Km plus S. Now, at steady state, the concentration of the enzyme, the concentration of the substrate is saturating, and it is such that the entire population of the enzyme molecules is converted in form of enzyme substrate complex. So at saturating concentration, the entire enzyme is existing in form of enzyme substrate complex, and when the entire population of enzyme is present in form of enzyme substrate complex, the rate of reaction is now the maximum rate of reaction. So therefore, this expression K2, which is the rate of the forward reaction, and ET, since the entire enzyme will be in form of enzyme substrate complex, and therefore the rate of reaction will be the maximum rate of reaction. So this expression K2 ET is given by the maximum rate of reaction for this enzyme catalyzed reaction. So the rate of reaction will now be given by this expression. Rate of reaction at any given interval of time at any given concentration of the substrate is equal to the maximum rate of reaction, which is represented by Vmax, multiplied by substrate concentration divided by Km plus S. This equation is called as the Michaelis-Menten equation. It is not important for you to remember the entire derivation, but you are required to remember the Michaelis-Menten equation. V naught equals Vmax S over Km plus S. Michaelis-Menten were the name of those people who deduced this expression. So the equation is named after them. We will now talk about one important significance of this equation. Let us consider a case that when the rate of reaction, the rate of reaction is half of the maximum rate of reaction. So we substitute this value here, that if the rate of reaction, if the velocity of the enzyme is equal to half of Vmax. So we put this value instead of V naught, that V naught is equal to the half of maximum rate of reaction. So when we simplify this, we get this expression by dividing both sides by Vmax. Half equals to S over Km plus S. So now we cross multiply this. So that would become Km plus S equals 2S. And we further simplify it by subtracting S on both sides. So therefore we get Km equals S. So now we have another mechanism to describe Km, that Km is equal to the substrate concentration when the enzyme catalyzes the reaction at half of the maximum rate of reaction, at half of the maximum velocity. So this is a more practical and an appropriate representation of Km. From the previous derivation of the equation, we have seen that Km was the ratio of the rates of breakdown and the rates of synthesis of the enzyme substrate complex. But here, in addition, we more appropriately describe Km as the substrate concentration at which the enzyme is operating at half of the maximum rate of reaction. This has a very important implication in terms of enzyme kinetics. Say, for example, if the Km for one enzyme is low and the Km for another enzyme is high, so that means if the enzyme has a low Km, the enzyme requires less amount of substrate to achieve the maximum rate of reaction. And if the Km for an enzyme is very high, that means the enzyme will require a very high amount of substrate concentration in order to achieve the maximum rate of reaction. So for example, that you are going to carry out an enzymatic reaction. Say you're working in a food industry and you want to carry out hydrolysis of starch, and there are two starch hydrolyzing enzymes available from different companies. One of those enzymes has a high Km, and the other enzyme has a low Km. So the enzyme with the low Km will be preferred because this enzyme can catalyze the reaction at a high rate by using a less amount of substrate. So therefore, the enzyme with a low Km will be useful in order to carry out this reaction because it can achieve the maximum rate of reaction by using less amount of substrate. This is diagrammatically represented here. This graph shows the substrate concentration on the x-axis and the rate of reaction on the y-axis. So this line shows the initial rate of reaction, and eventually the rate of reaction, it keeps on increasing. Eventually it becomes the maximum rate of reaction. So the substrate concentration at which, so we note the maximum rate of reaction, what is the Vmax, and then we look at the half of the maximum velocity, and this graph is then used to determine the Km. So Km represents the concentration of the substrate at which the rate of reaction is one half of the maximum rate of reaction. This table shows the Km value for some of the enzymes for various substrate. So you can see that, so these are the names of the enzymes: hexokinase, carbonic anhydrase, chymotrypsin, beta-galactosidase, etc. So these are the substrates of these enzymes, and the Km is represented here. So in most cases, the Km is in terms of millimolar of the substrate concentration or even submillimolar. So the previous example was with respect to carrying out an enzyme catalyzed reaction. However, the Km is also very significant with respect to various physiological phenomena. So we are going to look at this example here. Glucose is converted into glucose 6-phosphate, and ATP is the source of this phosphate. There are two enzymes which can carry out this reaction. They are one of the enzymes is called hexokinase, and the other one is called as glucokinase. Hexokinase is an enzyme which acts upon hexosis. Hexokinase can carry out the conversion of many different types of hexosis, whereas glucokinase is specific only for glucose. Both hexokinase and glucokinase can carry out this reaction, that is, they can carry out the phosphorylation of glucose to convert it into glucose 6-phosphate. Hexokinase is found in many different types of cells of the body, and glucokinase is mainly found in the cells of liver. Hexokinase has a low Km value, which means that this enzyme can carry out the reaction at a rapid rate when the substrate concentration is low. However, glucokinase has high Km, so when the glucose concentration is less, hexokinase is the main enzyme which is going to catalyze this reaction to convert glucose into glucose 6-phosphate. However, but when glucose concentration increase, now hexokinase is already saturated with glucose because it has a low Km, so its maximum rate of reaction is achieved at a relatively low concentration of glucose. So when the glucose concentration increases, hexokinase is now already saturated with glucose, and hence it is not able to utilize that additional glucose. This is where glucokinase comes into play. This is another enzyme which carries out the exact same chemical reaction. This enzyme is mainly found in the cells of the liver, the hepatocytes, but this enzyme has a high Km for glucose. So that means when the concentration of glucose is more and hexokinase is unable to utilize all that glucose because it is already saturated. So at high concentration of glucose, now glucokinase comes into play because this enzyme needs high concentration of glucose in order to carry out the reaction. So the uh, at high concentration, relatively high concentration of glucose, hexokinase becomes saturated and now is unable to utilize all that excess of glucose. So it is now the job of the glucokinase, which has a high concentration, which has a high Km, and hence operates at a higher concentration of glucose. So these two enzymes, they both carry out the same chemical reaction, phosphorylation of glucose, but they have different Km value. So this is physiologically very significant in order to carry out the chemical reaction at various different concentrations of glucose. Say, for example, under fasting conditions, the glucose concentration is low, but after consuming a meal, the concentration of glucose gradually increases. So therefore, when the concentration of glucose is high, it is glucokinase which can accommodate that high concentration of glucose by converting it into glucose 6-phosphate. So by having enzymes which catalyze the same chemical reaction, so the physiological significance of these two enzymes, which catalyze the same chemical reaction, but operating at different concentrations of glucose, is to accommodate and is to carry out the reaction under low and high concentrations of glucose. So in this way, the activity of these enzymes to carry out the same chemical reaction is regulated. Okay, so in order to accurately determine the maximum rate of reaction for an enzyme catalyzed reaction, it is if you plot it like this, it is very difficult to find the exact value of the maximum rate of reaction from this graph like this. So therefore, one important way to find the exact values of Km and Vmax, we use this reciprocal of the Michaelis-Menten equation. This is called as the Lineweaver-Burk plot. Sometimes it is also called as the double reciprocal plot. What we do here is that we take the reciprocal of this equation. So this turns into 1 by V naught, and this part of the equation will become Km plus S divided by V max S. So we have taken the reciprocal of this entire equation. So this equation, when simplified, is reduced to this expression, and this expression is called as the Lineweaver-Burk plot, the Lineweaver-Burk equation. And this equation could also be used to accurately determine the value of Km and Vmax through the following way: that we carry out the enzyme catalyzed reaction in different reaction mixtures by using various concentrations of the substrate. At every substrate concentration, we determine the rate of reaction, and then eventually we take the reciprocal of the substrate concentration and the reciprocal of the rate of reaction. Then we plot these reciprocals. The reciprocal of substrate concentration is taken on the x-axis, and the reciprocal of the rate of reaction is taken on the y-axis. So all these data points of the reciprocal are plotted, and then a line is drawn. The line is projected into the second quadrant of the graph. So the point where the line meets the y-axis, that gives the reciprocal of the maximum rate of reaction. And the point where the line meets the x-axis in the second quadrant, that is the reciprocal of the Km. So therefore, we find these two intercepts. The reciprocal of the y-intercept gives the maximum rate of reaction, and the reciprocal of the x-intercept gives the value of the Km. So by using the Lineweaver-Burk plot or the double reciprocal plot, we can more accurately determine the value of Vmax, and therefore can determine accurately the value of Km as well. Another important parameter to describe the kinetic efficacy of the enzymes is called as the turnover number. The turnover number represents that how much substrate is being converted into the product per molecule of the enzyme. Or, in other words, it can also be described as the, the maximum rate of reaction at which the enzyme is catalyzing the reaction, its ratio to the amount of the enzyme present in the given reaction mixture. So the turnover number, it gives the value that how much substrate is being converted into product by a given amount of the enzyme in a given duration of time. So that is called as the turnover number. If an enzyme has a high turnover number, that means the enzyme has high catalytic efficiency. If the enzyme has low Km value, that means the enzyme can operate at high rate of reaction by using less substrate concentration. This table shows the turnover number of some important enzymes. So these are the various enzymes shown here. These are the substrates, and this is the turnover number. So the turnover number shows that how many molecules of the substrate are being converted by one molecule of the enzyme per second. So it is a ratio of the substrate being converted by a given amount of the enzyme. So you can see that for catalase, this value is quite high, and for other enzymes, the turnover numbers are given. Greater the turnover number of the enzyme, higher is the kinetic efficacy of that enzyme. Another important way to describe the kinetic efficiency of an enzyme is to find the ratio of the kcat, which is the turnover number, to its km. Now, higher the turnover number, kcat, more is the kinetic efficiency of the enzyme, less is the km, so less is the amount of substrate required to achieve maximum rate of reaction. So therefore, taking the ratio of kcat, turnover number, to km provides a very useful number and shows the kinetic efficacy of the enzyme. If this ratio is high for a given enzyme, that means the enzyme is kinetically very efficient. And so that would be all about this topic of enzymes.